Okay, so let's get started. The last lecture before the Christmas break. And I want to finish today this analytic description of the free convolution. So we've started by looking on a compactly supported case, where essentially we dealt with moments and cumulant, and then we wrote these informal power series, and we could also consider those guys as analytic functions. But now, last time we went over to the case of general probability measures, and there our approach is mainly that we analyze the equation between quotient transform and R transform and try to find a solution for this. And as I pointed out we can do this. We did this last time. The R transform can be defined in some wedge-like regions, but it seems to be better to go over to an alternative description in terms of the subordination function. The subordination function on a formal level is equivalent to the R transform machinery, but it is described by a fixed point equation. And I showed you last time, at least by an example, that the solution of these fixed point equations seems to have nicer properties than the R transform, which is also the solution of some kind of equation, but not in this nice form. And today I want to make this more general and rigorous and give you somehow the outline of the main theorems there. I'm giving you the main ideas, but not proving everything. Okay, so we saw last time we can define the R transform, but now we really want to go over to look at the subordination function, and this is defined by a fixed point equation. So we want to investigate this equation. Investigate the fixed point equation for the subordination function. So the subordination fixed point equation, and this was the equation of the following form. So we had two subordination functions, but I mean things are symmetric by exchanging the two measures, and so if we solve for one of them, the rest is determined. Okay, so let's say omega 1 of z, that's our fixed point equation, that's our subordination function, and this is determined by the function z plus, and then I have here h nu, which is a variant of the Cauchy transform of nu, and the argument z plus, and then I have the h of the other measure, h mu, of omega 1 of z. Okay, so this is an equation for omega 1. Now omega 1 appears here and here. Okay, so this is our basic equation which we want to solve. And what we want to see is that actually for each set in the upper half plane, there's a unique solution of this equation, omega 1 of z, which is also has a value in the upper half plane. So what we want to see, this equation has a unique solution in the upper half plane for any argument set in the upper half plane. Not just for some domains in the upper half plane, but everywhere. I mean, if you go by the R transform machinery, essentially this shows us that at least in some domains we have a unique solution, because then we can write omega in terms of the R transform. Okay, but the point is we want to see this is everywhere. Good. Okay, so how do we solve such an equation? I mean, this is a fixed point equation, and of course it's a fixed point equation of a special map. So we should first note this. This equation is star. It's the fixed point. The mapping, where we just map something to this side of this something. Okay, so this we have the map, and we map W to this side here in terms of W, and of course W is now omega 1 of z. So W goes to z H nu of Z plus H of W. So that's a mapping in the complex plane where I set W, which is now W, where I set W to some other thing in W. What is an analytic map? And H, functions H are of course analytic mappings. And of course, if I have a fixed point of this mapping, then if omega 1 of Z is a fixed point of this mapping, then of course it satisfies this equation. And it means that this is the same as this. Okay, so we want a fixed point of a mapping, and of course, what is the most naive idea? If I have a mapping and I want a fixed point, okay, I'm just iterating it. Okay, I'm in the basic theorem, Spanner fixed point theorem. If we have enough control over our mapping, if it would be a contraction, then we know that iterating this mapping, I converge to a fixed point. Okay, so that's somehow a naive approach, but it turns out this works in this case. Okay, but by not so trivial reasons. Okay, so the naive approach for solving our fixed point equation is to iterate this map. Maybe I'm calling it double star. Please iterate this map and hope that this iterates converge to something. And then this something is of course the fixed point of this equation. And hope that this converges to the solution. Okay, and somehow surprisingly this actually works. Okay, but not because we have a contraction in the usual absolute value norm here, but because of some more, more deeper reasons. It's important that we have analytic maps here. So surprisingly, this works. And I want to give you some ideas why and also how this works and what we need. Okay, and as I said, this relies on the fact that it's not that we have here just some mappings, but we really have complex mappings, analytic mappings. So, and what we are looking here are essentially self-maps from C+ to C+, let's say. And such maps, analytic maps from C++ to C+, have a lot of strong, rigorous properties. This relies on the fact, that it works, relies on the fact that here we have analytic maps from C+ to C+. Of course, we still have to see that all those guys are really maps from C+ to C+. And for iterations of such maps, there are strong results. So, and for iterations of those, there are no strong results. So much stronger than you would just have real maps. Okay. Analytic maps are have much more rigorous properties. And actually, the two main ideas, the two main results, which we are going to use, are the following. Okay, so the first is that actually we know that at least for some set we have a fixed point. Okay, so we have a solution in some domain. The main point is that we want to see that we can extend this to all of signals. Okay, so the domains where we can work with the R transform, there we know that we have a solution. Okay, so in domains, the R transforms are defined. Let's say this is for set in some set omega in C+, so those are some open sets which are related to the wedges which we had. There we know that we have a solution. So it's important to do this R-transform machinery. So we have to know at least something at some points, at some regions in the complex plane. Okay, but so from the R-machine transform machinery, we know that we already know that there is the fixed point of our equation star. Okay, and then one can apply essentially a Schwarz lemma, which is an important lemma on complex functions, which tells us that then I also converge to this fixed point by my iteration. Okay, so at least somehow there it is automatic that if I have a fixed point, that I have to converge to this, which of course in general is also not true, but this is essentially after some conformal transformations in application the Schwarz lemma from complex analysis. I mean, the Schwarz lemma is something about mappings from the disk to the disk, and actually you also fix your mapping that f of 0 is equal to 0. But then it essentially says, so you have a fixed point at 0, but then the Schwarz lemma tells you essentially that you converge by doing iterations. Okay, and by convex transformation, I mean you can map the upper half plane to the disk, so they are conformally inverse. I mean that's the same, the conformal point of view, and you can also map your disk to itself such that you have a fixed point of your map. Okay, so essentially via conformal mappings, you are in a situation where you have an analytic mapping from the open disk to itself, which has 0 as a fixed point, and then the Schwarz lemma tells you that we converge. Okay, so an application of the Schwarz lemma shows iterations double star converge to this fixed point. So later I will be a bit more precise on this. At the moment it's just giving the idea. Okay, so this means that we have convergence, at least of our iterations, at least for some domain. Okay, but then there's another important theorem in complex analysis, which is about the convergence of sequences of analytic functions, and this is Vitalis' theorem, which tells us that I have convergence of the sequence of functions in some nice, let's say, open set, then actually it converges everywhere. Okay. So the second point is somehow extending the fact that we know we have convergence in some region to all of C++. And this is given by Vitalis' theorem, which is a consequence, or actually equivalent to Montel. Montel is something which you should have. But in any case, the complex analysis, the theorem of Vitalis is a consequence of this. Okay. So if we have convergence of iterates, at least for set with some nice domain, open set. I think it would be enough if we have a set which has a cluster point somewhere. Okay, so we have it for this. Then this other nice theorem for complex analysis, namely Vitalis' theorem, shows that actually these iterations converge everywhere, also for all settings. Then this shows that we have convergence of iterations actually everywhere. Actually, set in C++. And of course the limit of these iterations is then a fixed point. Okay, and this means we have a fixed point everywhere. And of course it also has to be unique. The limit of these iterations, or then omega 1 of z, is then the unique fixed point equation. Good, okay. And I mean, in the following I want to make this a little bit more precise. In particular, for example, for a Schwarz lemma, one should be a little bit careful because I mean self-maps of the disk to itself, which fix the zero. I said the Schwarz lemma tells us that these iterates converge, but this is only the case if we exclude special maps. And then of course we also have rotations of the disk. This has a zero as a fixed point, but of course I mean if I iterate by rotations I'm not converging to the fixed point. But the rotation is an automorphism of the disk. Okay, for automorphism, so the Schwarz lemma doesn't tell us that we have converged. Okay, so in particular we have to exclude the mappings which you consider are automorphism of the disk, or I mean, in our case of the upper half plane. So that's important that we can apply. Get the right conclusion for the Schwarz lemma. So maybe we say this here. That's what we use. Schwarz lemma in point 1 should exclude the map or fixed or iterating map is an automorphism. So this means a bijective map which has an inverse. The inverse is also complex. So in particular we should exclude that it is a bijective mapping. Okay, it's an automorphism in our case of C+. Okay, so we should keep this in mind that we have to do this. Good. Yeah, but now maybe I should start to get a little bit more concrete on this. But this is the problem. So in principle we have to do this. All this can be done nicely. Okay. So maybe do it precisely. Maybe let me use the notations which are already introduced before. I mean, in our fixed point equation we have this map H. Let me just recall what this is. If I have a probability measure, no assumption on moments or compact support or anything, just an arbitrary one. And of course this has a quotient transform, which we call, as usual, G mu. But then out of this quotient transform, we get some other mappings, which are this mapping H, and as an intermediate mapping which we call F. So then what we consider are variants, easy variants of G mu. I mean, you can say the R transform is also a variant of the quotient transform, but it's a complicated one because you have to take the inverse under composition. Here we just do easy. We take 1 over the quotient transform, which is easy to control, and this is what we call F. So F mu of z. This is 1 over G mu of z, and H is F, and then I am subtracting also z. So H mu of z, this is F of z minus z, which in terms of G is 1 over G mu minus z. Okay, and so those are the functions. In particular, H is the function which shows up in our subordination fixed point equation, and so we should think a little bit what kind of mapping this is. Of course, they are all analytic mappings in the argument whenever G and 1 over G makes sense. So G is defining the upper half plane, and then all those expressions make sense. Huh? So I mean, all those functions are analytic functions for all set in the upper half plane. But we should also see where are they going. Okay, so they are analytic for set in C++. So they are all defined in C++, but where are they going for? And of course, I mean for G, we know. So the Cauchy transform goes from C plus to C minus. Okay, and then if I take 1 over the Cauchy transform, I mean taking 1 over Z maps the upper half plane to the lower and the other way around. Okay, so if I take 1 over G, so G goes from C plus to C minus, and if I take 1 over this, then I'm going back to C plus. Okay, so this means this F really is a mapping from C plus to C plus. Mu is from C plus to C plus. Okay, for H mu, it's not so clear because I mean, of course, this goes to C plus, but then I'm subtracting something. This could mean that I'm falling into the lower half plane. Okay, but of course, what I really want are mappings on C plus, so I really want to see that this is also going to land in C plus. Which means, of course, that the imaginary part of this guy should be bigger than the imaginary part of this guy. So if I take the difference, I'm not leaving upper half. Okay, so that's the thing we should see, that this is true. So maybe this is a lemma, we're going to prove. That this F transform has this property that it increases the imaginary part. Imaginary part of F mu of Z for all sets in the upper half plane. And this is in principle good because it tells us that we are not falling into the lower half plane. But of course, if we have equality there, then of course then this difference is on a real axis, and of course that's also what we really like. We want mappings from C plus into C plus, not onto the boundary. So at least we should understand whether it can happen if we have equality. So equality is also not working. And it turns out that actually equality is a very special situation, namely the situation where we have a Dirac mass. Okay, a measure which has only one atom at some point. So here, equality for some set only if mu is Dirac mass. Also, this means mu is of the form delta of A. No? It's a Dirac mass at A. Okay, and of course, so if we have this means if mu is not a Dirac mass, then this mapping H really is a mapping which goes into the upper half. So, as we have, that H mu goes from C plus to C plus if mu is not if it is a Dirac mass, so if it is delta A, then actually, I mean, we can calculate very easily what H is. Then it's also something which is not so bad. So if mu is of the form delta A, then we have H mu of A of Z. Then it might take one values on the real line, and actually it does it for a set. So maybe that it is constant equal to minus A or Z and C plus. Okay. Good. So let us prove. The main thing is the first part is inequality for the imaginary part. But this is essentially a calculation. I mean, for the Cauchy transform, we have our integral formula, and then we just have to see This gives us the imaginary part, and then of course we have to do some estimates. And this estimate in the end is just Cauchy-Schwarz. Okay, so let us do the calculation. And of course, I mean, this is just about one measure, so I omit the mu as an input, so just use G and F. Good. Okay, so what do we have? So I want to get the imaginary part of f of z. F of z is 1 over g. I want the imaginary part of 1 over g of z. Good, so how do I get this? And of course, I write this and multiply this with g of z times g of z star of r, complex conjugate, and here complex conjugate. So I'm writing it in such a form that this is just a real number, and then the imaginary part is just the imaginary part of this here. Okay, so what I have here is then of course, this is the absolute value squared of g, and the imaginary part of g bar is minus the imaginary part of g. So minus the imaginary part of g of z divided by g of z squared. Good, so this means I should now take the imaginary part of g, but g was given explicitly as an integral, so I can continue, is minus 1 over g of z squared, and then I take the imaginary part of g, and g was this integral, so I'm moving the imaginary part under the integral, and I have here 1 over z minus t ddt. So g of z is integral over 1 over z minus t du, and I take the imaginary part. And again, what is the imaginary part of this? Again, I multiply it with z bar minus t here, and then I also get it here, and then the imaginary part is the imaginary part of z bar, which is minus the imaginary part of z. So what I get here is minus the imaginary part of z divided by z minus t squared. Okay, so in the end, what I have is, let me see, I have a minus here and a minus here, so this cancels. I have the imaginary part of z divided by g of z squared and multiplied with this integral. I mean, this goes out, so I have 1 over z minus t squared dut. Okay, what we want to show is that the imaginary part of f mu of z is greater or equal than the imaginary part of z. Or to put it the other way is by dividing the imaginary part of f of z by the imaginary part of z, and this is nice because this is here, so I bring this on the other side, then I have to show that this is greater or equal than what is left here. Okay. So what we have to show is that actually this divided by this is greater or equal than 1. So if I bring this on the other side, I have to show that g of z squared is less or equal than this one. It's less or equal to the integral 1 over z minus t squared d mu of t. Okay, well now hopefully you see that this should be a consequence of Cauchy-Schwarz. Because I mean, this integral is essentially integral of this form without the square. that's what we have to show. And this follows because what do I have on this side? This is the absolute value of the integral 1 over z minus t d mu t. That's a Cauchy transform, the square of this, and by Cauchy-Schwarz. So this is the inner product of this function with the function 1 in this L2 space. So Cauchy-Schwarz for the L2 space of mu, that this is less or equal than the integral of 1 squared dt times the integral of the square of this. So here I'm writing this as 1 times this, and then I'm estimating it against the square of 1 and against the square of this. So this is 1 over minus t squared and of course, mu is a probability measure, so the integral of the function 1 is just 1. Okay, so what I have here will be 1 over z minus t here squared d mu of t. Okay, and so that's the general inequality. And when can I have equality in Cauchy-Schwarz? This is when the two functions which are involved are linearly dependent. So this means equality here can show up if the function 1 and the function 1 over z minus t are linearly dependent in L2 of mu. But this means, of course, that the function 1 over z minus t must be constant, almost surely with respect to mu. And this means, of course, that mu has to be a Dirac measure. Okay, so yeah. Okay, so this shows then also part. Okay, and then, of course, the second point is then also clear. I mean, if I don't have a Dirac measure, then I have a strict inequality here, and then of course I can estimate the imaginary part of h. So this is the imaginary part f of z minus the imaginary part of z. H was f minus z. And if you don't have a Dirac measure, then this here is strictly greater than the imaginary part of z, according to what we just showed. So this means this here is greater than 0. The imaginary part of h is greater than 0, which means h is in the upper half plane. Okay, and this is true for all set in C+. From C+ to C+. Okay, and if we have a Dirac measure, then of course we just can calculate what h is. So if mu is a Dirac measure for some AR, so it's grade 1 at the atom A. And then, of course, what is the Cauchy transform? What is then G mu of Z? So I'm integrating 1 over Z minus T with delta of A, but this means I just have to put T equal to A, and I'm just getting 1 over Z minus A. Oh, okay. So that's a Cauchy transform in this case. Then the F transform 1 over the quotient transform. So this is z minus a. And now if I'm subtracting z to get the h transform, then I'm just left with minus a. So this means the h transform is just minus a. Oh, okay, so you see it's a constant function. Oh? So this case is a mapping from C plus to the closure of C plus. It actually takes on only one value, namely minus a, which lives on the real line. Good. Okay, so we have, and I mean this mapping H is the one which shows up in our fixed point equation. Okay, now maybe we should also give a name to the mapping for our iterations, and then we should investigate this mapping, because that's really the one which you have to understand. So now we really go over to our equation. Okay, so the following, I will always fix two measures, mu and nu, for which I want to calculate or define the free convolution, and this I want to do by solving the fixed point equation. Let's see. Yeah. Okay, so that's our notations. So we have now two measures, mu and nu. Two probability measures for R. And then we want to consider now the function which gives us our iterations. So the right hand side of our fixed point equation. And so I want to do this for any set, and so for any set in C plus, consider this function, which is an analytic function of course, and I call this G set. G is a subscript set. So set is here, let's say, constant, and for each set, G of set is a function from C plus. 2, of course, let's hope to C plus, but okay, at the moment maybe we don't know, so let's just say C, which is defined by that W goes over to G set of W, and this is now what appears in our fixed point equation. So this is set plus H of the second measure, and the argument is set plus H of the first measure, H mu of W. So this is a mapping. So set is here considered as a, you can say, parameter. So for each fixed set, I have this function here as a function in W. And the W shows up here again. But the set also shows up as a parameter. And what we want to do is for each set, we want to see that this function has a fixed point. And this fixed point, of course, then depends on set. But I mean, to get the fixed point, we want, for fixed set, we want to iterate this function. Okay. So first we should see that really this is a function from C plus to C plus, so that we really have a self-mapping of the upper. So according to what we have seen here, this is now clear. Let's write it down. This is another lemma. So namely we have for all those functions, so for all sets in C plus, that G set is really a function, analytic function from C plus to C plus, and furthermore we should also exclude the case which I said is problematic in the application of the Schwarz lemma, namely an automorphism. So we should exclude that this is an automorphism from C plus to C plus. Okay. this is also part of this lemma. So G set is not automorphism. And indeed, to see this, I mean, it's enough to see that it's not bijective. And for this, it is enough to see that the upper half plane is mapped to something which is not all of the upper half plane. And this we can see if we have the estimate that G set of W is always greater or equal to the imaginary part of Z. So I mean, this is the imaginary part of Z, which is fixed here. So this means we are mapping the upper half plane onto something which has imaginary part bigger than the imaginary part of Z. So here, the imaginary part of Z. Okay, so if we have this, if you see this, then we see that G set is not bijective mapping, and then it cannot be automorphism. Okay, and this is easy to see from the estimates which we have seen before. Okay, the only thing which we have to see is this inequality. This tells us that we are going to C plus, and actually we cannot go to all of C plus. So let us just check this. So we have the imaginary part, G set of W. So what is this? I mean, G set of W is defined here. So I take the imaginary part of this, so this is the imaginary part of Z, plus the imaginary part of H nu of Z plus H nu of W. Good. Okay, so I mean this Z plus H mu of W, of course this is in C plus, because we have seen that H is a mapping from C plus to C, or maybe in a special case that I have a Dirac mass, it could also be a real number. Okay, but Z is in the upper half plane, so I mean this is in any case, even if I have a Dirac mass here, this is in the upper half plane, so this means this here is in C plus, and this means I can apply H nu to it. So this is something one should think about it, to see that this really is well defined as a function of in all of C plus. Okay, but this is in C plus. And again, we know is H nu, the imaginary part of this is greater or equal than 0. Again, generally it is greater than 0. In the case of the Dirac mass, it could be on the real line, but it doesn't care. If this is good enough, so this imaginary part is greater or equal than 0, and so this means we always have this as a lower bound for this. So this here is greater or equal to the imaginary part of Z. Yeah, which is a constant if I'm fixing myself. My variable is done. Good. Okay, so this tells us that, yeah, really this G of Z is a nice self-mapping of the upper half plane, which is not an automorphism of the upper half plane. And this means we can apply this Schwarzschild. Good. Okay, now maybe we just go, let me make a precise statement about these fixed point things, and then give you not all the details, but some more details about the proof. So making that what I gave you at the beginning, and essentially we have to use Schwarzschild and we have to use Vitali, make this a little bit more precise. Let me also make the statement more precise. So this is the main theorem. Okay, and then we are looking on this function gz of w, which was defined before, and then we are claiming something about fixed points. So then the function gz, which we just have seen, is a function from C plus to C plus, which maps, of course, w to gz w. The precise formula is here. Okay, so this function has, so for each set in C plus, so we have here a collection of functions. For each set in C plus, I have such a function, and I say each of them has a unique fixed point. Unique fixed point, and I call this now W, and of course it depends on Z. So for each Z, I have such a fixed point, so I call this, well, I call it omega, let's say, omega of Z. And this fixed point, of course, is also in C plus. Okay, and actually, there's also a concrete way how to get this fixed point, namely by iterating our maps. So this omega of Z is given by iterating my maps, and I can start wherever I want in the upper half. So this also shows, of course, that the fixed point is unique. Because I could, if I would have two, I could start on any of them. Okay, and so this is given by omega of Z, the limit n going to infinity of g of Z, and then I'm iterating this function n times. So this means I take composition of this function with itself n times, and I do this at some argument set 0, which I can choose arbitrarily. Any set 0, of course, in the upper half plane. I must start in the upper half plane. I have a map which maps the upper half plane into itself, so I get a sequence of points in the upper half plane, but I'm claiming this converges, and this actually converges to my fixed point. Okay, so this here composition of g of Z, and furthermore, of course, the dependence of this fixed point in Z is analytic. That's also good. So now I consider this omega really as a function in Z. Up to this point, Z was just a parameter which I put in my equation, and I solve this equation for each of those parameters. The solution depends on this parameter. This parameter is also a complex number in the upper half plane, and now the statement is actually this dependency on this parameter is also analytic. So the function omega is now a function for C plus. So for each set, we have such a fixed point which lives in C plus. So this means Z is now going omega of Z, and this function is also analytic. Okay, I mean that's all we want. All we need. So that's a crucial theorem for establishing a free convolution. Good. Okay. And I mean in this form this is really going back to Wilinski and Berkovich. That's the approach. That's good. Okay, so let me give you the main steps in the proof. Okay, so maybe I have erased the formula for GZ, so maybe I write it down again here. So the GZ W, this was given by Z plus H nu Z plus H nu. Okay, but actually the precise formula is not so important now anymore. It's just that we have here a mapping which is not an automorphism which maps the upper half plane to itself. Okay. Good. Yeah, so what is the idea? I mean, of course, in principle, we want to get right away, I mean, our function omega of z by iterating just this g of z. And consider this directly as a function in z. I mean, this, of course, is also an analytic function in z. So this means I can take this function and then iterate it, and then I have a function in z, and I hope that this converges to something. And as we say in the theorem, we can choose an arbitrary starting point of our iteration. Right? In the end, it should not matter. So let us do this. Right? For all z, we can choose the same one. So we choose arbitrary initial point. Maybe I call it u0 in C plus. Just any point. You can take your favorite point in C plus. So we choose this for our iteration. And then we define a sequence of functions fn of z by saying this is g of z, taking the n-fold convolution of this with itself, composition with itself, and apply this to u0. Okay, so I take, if I want fn of z, so this means in particular f1 of z, this is just gz, so this is just this here, but applied to our point u0. Okay, and then f2 is applying gz again to this point, and so on. So this w is now just the u0 and the iterates of this, but now I consider this really as a function in z. So I have this fn of z, and each of those guys, fn, is an analytic function in z. Because it's a composition of analytic functions. And all of them are going from C plus to C plus. Each fn is an analytic function. So fn goes from C plus to C plus. Because we know that gz of w for any value of z and any value of w is in C plus. And we consider this and it iterates as functions in z, and the dependency is analytic. Of course, because those are analytic functions. Good. Okay, what we want to see is that this, so this is now a sequence of functions, sequence of complex functions, and we want to see that this converges, and that it converges everywhere. So we want to see that the sequence of n and 1, so a sequence of complex functions on the upper half plane, that this converges to a limit function. This limit function is what we are going to call omega, and of course, if this convergence is the usual convergence for analytic functions, uniform convergence in compact sets, then actually we also know by the usual theorems that this limit is also an analytic function. So again, it's these very strong properties of analytic functions. Good. Okay. And now we follow the procedure which I told you before. So first of all, we see that at least we know that we have a fixed point of our mapping in some domain. Okay, so this is by the R transform machinery. Right? By the R transform description. We know in some domains of the upper half plane that we have essentially a solution to our equation. So because last time formally I showed you that the description via R transform can be reformulated in a formal way as in this fixed point equation. And these formal manipulations can be made rigorous on the domains where really the R transform were analytic functions. Okay, so by the R transform description, know that at least for some set we have a fixed point. So know that there is a set omega in C plus, a subset of C plus, such that for the sets in this set omega, the function set from C plus to C plus as a fixed point. Okay, so we have a solution for the fixed point equation. Good. Okay, a priori, this doesn't necessarily tell us that iterations converge to this fixed point. Okay, but now we use this Schwarz lemma, which tells us that this is actually somehow the same. Also, you see, I mean, we have a solution of this equation, and on the other hand, we have iterates of our function. And of course, the idea is that those iterates should converge to this solution. Okay, but I mean, we have to go back and forth between these 2 points. I mean, here we know actually that we have a solution, and we have to see that this is really the limit of the fixed points, the limit of the iterates. And then, I mean, if we want to extend it, this from omega to all, I mean, we are not talking about fixed points anymore, but we are talking about the convergence of this. If we know that this converges somewhere, then we know it converges everywhere. And then it has necessarily to converge to a fixed point. Also, it's going back and forth between the fixed point equation and the iterations. Good. Okay, so but here we know that we have a fixed point, and then it's the application of the Schwarz lemma. And then the Schwarz lemma for complex analysis, this implies that for those complex numbers set in omega, those iterates G set composed n times, if I apply it to any starting point, for example to this point u0, that this converges to this fixed point. And of course this fixed point is then necessarily B. Okay, good. And I mean, if you are going to look up or recall what the Schwarz lemma tells you, this actually is about self-maps from the disk to itself, where f of 0 is equal to 0. And here it looks in a much more general situation, but by conformal mappings, you can first map the upper half plane to the disk, and then you can also do an automorphism of the disk such that, that your fixed point is at 0. Via formal transformations, one can map the upper half plane. I think that's where we are working here. One can map this C plus to the open disk, let's say D. So those are the complex numbers whose absolute value is strictly less than 1. And I mean, this mapping is Möbius transformation. You can really write it down very explicitly. So you can map this to the disk, and then actually you can assume, if you are there by doing some other transformations, that the functions, you have some transform the g of z, you map this to some other function from this to this, but you can assume that the fixed point is really 0. Okay, good. And then you have a map from the this to itself, at 0 is 0, and then the Schwarz lemma tells you that actually something about the absolute value, that this must shrink in most cases. And the only case where it does not shrink is if you have an automorphism. Then you have somehow rotations. Okay. So then you apply essentially Schwarz lemma to this. And in order to see that you really converge with your iterates, you need in the inequality, in the Schwarz lemma, you need strict inequality, and this is guaranteed if your mapping is not an automorphism. But that's the case. No? I mean, the g of z is somehow the mapping of our g of z from the upper half plane to itself, and there we saw it's not an automorphism. No? So also if we transform this into the disk, we have something which is not an automorphism of the disk. And Twiddle. Good. Okay, so that's the first part. So this really tells us by what we did with the R transform, we know that we have a fixed point, but then this application of Schwarz lemma tells us that actually our iterates must converge to this fixed point. Good. Okay, and this means that our functions Fn converge at least for z in the set omega. So this was an argument where we know something, not for all z in the upper half plane, but only for some special ones, which are in some set omega, which is it's good enough to know it's open, I guess. It has some cluster points. Okay, so what this tells us, hence we have our sequence of analytic functions in the upper half plane converges, maybe not everywhere, but at least on the set omega. Good, but then we can apply Vitalis' theorem, which tells us that sequences of analytic functions, maybe let's say again from the disk to the disk, which converge on some set, let's say which is open, has to converge everywhere. Okay, so this means if we know convergence on the set omega, this is enough to get convergence everywhere. So this is Vitalis' theorem, which is a consequence, I mean, Montel's theorem. That's something which you should have done in any case in complex analysis. And Vitali is a consequence of this, but actually it's equivalent. One implies the other. Good. Okay, so this is about the normal convergence for normal families of the complex functions. So it's talking about the convergence of analytic functions. Okay, so then this Vitalis' theorem implies that actually this sequence converges everywhere. That this implies that n converges everywhere, and this convergence is a normal convergence, so uniform and compact subsets, and this means the limit of a sequence of analytic functions, and this convergence is also analytic. So we also get that the limit is an analytic function. So this converges to an analytic limit function on all C plus. Okay, of course we call this omega, so what we are saying here is, so there is analytic limit by the fact that limit fn of z, if n goes to infinity, for any set has a limit, this is the omega of z, for all z in C plus, and as a function z, this is really an analytic function. Good, okay. And I mean, one has to exclude somehow that this limit, I mean the fn's are mappings from the disk to itself, so they are all in the open disk, but of course if you have a limit, this might land on the boundary. So you have to exclude this, but this is the maximum principle that the maximum can only be attained on the boundary, and in this case your function had to be constant. Okay, but we know that this function here is not constant because you can see that it cannot be constant on this set omega. Okay, so you have to exclude that somehow you get a constant function in the limit. Okay, but this can be excluded because we know this is not constant omega, and so this means we really have here a function. This omega really is a function from C plus to C plus. We are not touching the boundary because of this limit. The limit could live on the boundary, even if all the elements are inside the set. So this is something which one also has to exclude, but which also follows from the usual theorems. Good. Okay. So we write this down here. Okay, so what I just said, so this limit is not constant. Since it is not constant on omega, and there we have quite some more information about our functions, and this implies then that omega of z actually has to take really all its values in C plus. Also in C plus. So this means our function omega really is a mapping from C plus to C plus. And of course, it is now, it satisfies the fixed point equation because, and this is somewhat clear, if I have the limit of iterations, if it converges, then this limit must satisfy the fixed point iteration. So, of course, we have gz of omega of z. So, what we have seen, and this omega of z is the limit of compositions of Gn with itself from some starting point. Okay, but now I apply gz to this limit, everything is continuous. So this means this is the same as the limit infinity. If I'm applying gz to this here, but this just means instead of the n-fold composition, I have the n plus first fold conversion. Okay, but of course, I mean, this converges, of course, again to omega of z. So this means omega of z really satisfies our fixed point equation. Thus, omega of z is our fixed point. And of course, it's necessarily unique. Statement is also, I mean, I can take any initial point and I converge always to this omega of z, and if I would have two fixed points, I could start at any of them, and I can, okay. In the end, they must be the same. Good. So this is the crucial point for defining or dealing with the free convolution in the general case. Because if I have solved now this fixed point equation, if I have my omega offset, I can use this for defining the Cauchy transform of the free convolution according to the formulas which we had. In the beginning I reformulated the description which we wanted in terms of omega 1 and omega 2, but we saw we only need one of them. And if I have this omega, then this determines all the rest. So maybe let me just point this out. Of course, one still has to prove a few things about the subordination function, that it has the right properties, so that in the end the free convolution is also a probability measure. This is a small remark. Okay, so let us start again. We have two probability measures, given mu. If we want, basically you can say we already defined the free convolutions, the R-transform machinery. But we can also maybe do the following way. So if I have this, then we determine the subordination function by this data. So we determine omega 1, which is this function omega here, according to 5.11. So we know there is a unique solution of this equation, and we know how we can get it. And this is really a function from C plus to C+, and then we can use this for defining or describing the Cauchy transform of the free convolution. Because what was the purpose of the subordination function? It should subordinate the Cauchy transform of the free convolution to the Cauchy transform of one of the starting measures. Okay, so this means the Cauchy transform of the free convolution. This should now be given as the Cauchy transform of the measure mu, and then we should plug in this omega 1 offset. That was the relation from which we started when we introduced the subordination function. Okay, now you can say, okay, two measures, we determine this here, and then we define this G offset, and this G offset then is the Cauchy transform of our free convolution. Okay, so in principle, this is exactly how it works. But of course one has to check that the function which we get here is really the Cauchy transform of something. This might also not be so clear. The Cauchy transform is, we have characterizations. Any function, the Cauchy transform must have exactly the properties. It's a function, an analytic function which maps the upper half plane to the lower half plane, but it should also have some condition at infinity, some growth condition. Okay, and the mapping is okay. The upper half plane, here it goes to the upper half plane, and this maps it to the lower half plane. So it's really all are analytic functions. So this is really an analytic function from the upper to the lower half plane. Okay, but we should also see that if z goes to infinity, that we get the right behavior there. And this means if z goes to infinity, this thing should go to infinity in the same way, because then we can use the corresponding property of this. So this means we need some property of omega, which one can show, which is a bit technical, so I'm not going into this, but at least there's something to do. It shows then that omega 1 satisfies omega 1 if I go to infinity, and usually it was enough to control what happens if I go along the imaginary axis. And then, G should behave like Iy there, and this means omega should also behave in the same way. So this limit here should be equal to 1. But that's something which one can show. And if one has this, then this implies that G, defined in this way, really is the Cauchy transform of some measure. This implies G also has to be at infinity, and then it must be the Cauchy transform of some measure. And of course this is the measure which is then the free convolution of mu and mu, so which we know by mu plus mu. And of course this has then exactly the property that the R transforms are additive where they are defined. Because this additivity of the R transform was formally the same as the subordination equation. This has property that R of mu plus mu of z is the same as R mu of z plus R mu of z, where those dies are defined. Of course, the R transforms are only defined in these wedges. Okay, maybe in different wedges, but we find at least some where this makes sense, and then we have this here. Okay, of course, this means, in the cases where we already know the theory, for example, in the compactly supported case, we just recover what we did there, because then the definition of the of the free convolution was also equivalent to this. Okay, so this is really an extension of the theory which we had before. But of course, it also means that also in the compactly supported case, we can describe the whole theory by the subordination function, which might be, even in this case, nicer for doing concrete calculations or numerical calculations. If we can solve the equations by hand, then of course we have a nice solution. But very often these equations, either the R transform equations or the subordination equations, don't have explicit solutions. And then you have to numerically solve them. And the subordination theory tells us exactly how we should do it. So we just iterate our function. This is very easy. It can be done very easily numerically. Solving the function for the R transform, it's not so clear. There we don't have an iteration procedure. So yeah, it's not really. So this means the subordination formulation is usually, in particular in a case where we don't have explicit solutions, is much better. Not just from an abstract analytic point of view, but also if you want to do concrete calculations, numerical calculations. Okay, so maybe let me do one or two examples, easy examples, just to see. It's a bit hard to see concrete things with measures which have no concrete support. Or even no moments. It's not so easy to have concrete measures which have no moments. Maybe the first thing is something where we take the free convolution with a delta function, with a delta measure. That's we know in a compact case, this is just a shift of my measure. And so, of course, this should also be true in this general situation, but maybe we should check whether the theory really gives us those. So, what I want to do is I want to calculate the free convolution of any measure with the delta measure at A. So, in principle, this is the sum of the operator with a multiple of 1. Which of course should just shift the distribution. And we know in a compact case it does this. So what is here? Okay, so what we need is the so we want to do the subordination formulation. So we need the H function, and so the mu is here the delta A. And so in particular I want the H function of this. But that's so the H function of Dirac measure, that's something what we calculated before. This was a constant function. And that was the situation where our function is constant and actually takes on a value on the boundary of the upper complex plane. So namely the delta function in this case is just minus a. Okay, but this means, yeah, this is our determining equation for omega 1 of z. This is determined by, yeah, our equation is omega 1 of z in general, so it's a fixed point of this g set of omega 1 of z. And now what is g? This is z plus h, and then we have here some argument, but this h nu in our case is just a constant. So this argument here doesn't matter, so what I get here is just minus a. So I have here that this is just z minus a. Okay, and so we have to look for, this gives us directly what this is. So namely omega 1 of z, in this case, is just z minus a. Okay. A is a real number. Okay. So this really maps the upper half plane to itself. I mean, I'm really just shifting in the vertical. Horizontal direction. And I'm not shifting downwards. So this looks as a verb. Okay. Good. Okay. So this is mapping, and this tells us that the Cauchy transform of mu plus delta of a. So this is the Cauchy transform of mu, and then I have to take the subordination function, exactly this one, omega 1. Omega 1 of z. In this case is just z minus a. So this means the Cauchy transform of this new measure is the Cauchy transform of this just shifted by a. And this also means that the measure is just shifted by the amount a. If you use this inversion formula, you see what you get here is the same as what you get here, just shifted by the amount a on the axis. So we have here in general what we already knew, at least in the compact isopolyp case. Hence, the free convolution, anything with a delta measure a, the element a, is also in general, for general mu, a shift of measure mu. Okay, maybe I want to make one last example where we really take the free convolution is an unbounded measure. Oh, okay. Of course, you can say, okay, here it's about this measure. What about this? What I really did here? So it's not really the convolution; it's unbounded. Okay, but now let us really take a real unbounded one. And there is one unbounded measure which is quite explicit and which has almost no moments, and this is the Cauchy distribution. Also, maybe. Let us check what we get in this case. What can we say about this? Because the Cauchy distribution is also something which is very often used in classical probability theory, or in many cases to make things smooth. Convolution with a Cauchy transformation regularizes many situations. And so let us see what is the free convolution with a Cauchy. Consider now the so-called Cauchy distribution. Important probability measure for classical probability theory. And this has a density, so this is a mu. Specifically, it has a density of t, so this is 1 over pi. The density is 1 divided by 1 plus t squared dt. So this looks somehow, it's unbounded, and it but it has long tails. I mean, the Gauss distribution goes down exponentially for large arguments. This here only goes down polynomially. Okay, this is the reason that this measure has no moments. Okay, it has the first moment is 0 because it's symmetric, but the second moment and higher moments don't exist at this guy. It's an important distribution. Okay, so what do you need to see, to talk about free convolution is this. Okay, we need first of all the Cauchy transform. So what is the Cauchy transform of this? The Cauchy transform of the Cauchy distribution, so what is this? Okay, so I have to integrate 1 over z minus t with respect to this measure. So I get 1 over pi, and then I have to 1 over plus t squared dt. Integrate this over r. Okay, and this is now an integral, which a priori is not so clear what this is. But again, we can use complex methods, residual theorem, to calculate this. So essentially, you want to integrate over r, but what you're doing is you integrate, let's say, over the lower plane, and going in the big circle. Essentially, those things will go to 0, and so what you have to calculate is the residue of this function inside this domain. The residue in t. Okay, and I mean, z might be a residue, but z is in the upper half plane. That's why I went to the lower, so of course also to the integral in the upper one. But so z is not a residue, so this term will not contribute. And then I have my plus and minus I. I have a residue, and this is inside this, so I have to calculate the residue of this function at minus I. And if I do this, what do I get here? I get 1 over z plus I. Okay, so we get a very simple and nice result. And actually what we get looks like the Cauchy transform of a delta function at minus I. But of course it's, okay, so it looks as if I would have a delta function sitting here, but of course it's a probability measure on a real line. But from the point of view of the Cauchy transform, it behaves like this, which means for our free convolution, it behaves also like the convolution with is a delta function. Okay. And so in particular, the H and the F transform are like before, so namely H, this is 1 over G, so this means I have Z plus I, and then I have to subtract Z, so I just get Z plus I, this is 1 over G, and then I'm subtracting Z, so I just get I. So again, I get a constant, but now this constant is not on the boundary, but it's really in the upper half. Oh, okay. And what is now my fixed point equation? So what is the G, Z, W? This is now again Z plus the H transform of this, that's some argument, but the H transform is always I. So I get here Z plus I. So this means my omega of Z is here just Z plus I. So again, it's just a shift of my argument, but now it's really a shift in the upper half plane, in the vertical direction. And so this means if I take the free convolution of anything with this specific Cauchy distribution, then the Cauchy transform of this is just the Cauchy transform of mu and shifted by the amount I. And this is okay. I mean, Z is in the upper half plane, then I'm adding I, so I'm just moving more in the upper half plane. So that's okay. Okay. And yeah, now you can think, what is this? What is this? And if you look on this, actually you will see that this is actually the same result as the classical convolution with a Cauchy distribution. Because if you look on corresponding formulas for classical convolution, you can check this. So it turns out that this is the same result as the classical convolution. With in this respect, it behaves like a delta. Because I mean, a delta, of course, if I take a convolution with delta at point A, this gives me the shift of the measure by A. Of course, in the classical world, this is the same. So the classical convolution and the free convolution with delta distribution have the same effect. But here it turns out that also with the Cauchy distribution has the same effect. And there it's not so obvious. Right? It's absolutely not clear why this should be the case. But it turns out, it comes out of this machinery. And formally, I mean, of course you can say it's the case because the Cauchy distribution is somehow like a delta function, behaves in many respects like a delta function at this point I. Good, okay, but this also means that somehow this Cauchy distribution, the free analog of the classical Cauchy distribution is actually the Cauchy distribution itself. So I mean, what you would call a Cauchy distribution in the free world turns out to be the classical Cauchy distribution. Right? It's not just the analog, but it's exactly the same. So I mean, in the classical world we have the normal distribution and we have a free analog of this, but this is the sinusoid. So there is something which plays the role of the classical normal distribution, but of course it's a different distribution. Okay, but for the Cauchy distribution, so we have in the classical theory, we have the Cauchy distribution. I mean, you can characterize this in many ways. It's a stable distribution of something, and the same stable distribution in the free world is actually the same Cauchy distribution. Right? I mean, this is exactly this here. The free convolution with the Cauchy distribution is the same as the classical convolution with the Cauchy distribution. This is something which is not so clear. That's the case. Okay, so anyhow.
But can we find marking the front variable having this distribution? So is there a random variable having this distribution?
Yeah, I mean on the L2 space with respect to this measure, you can take multiplication with x. This is an unbounded operator, but this has exactly this distribution. I mean, you can realize all probability measures, you can realize them as canonical unbounded operators on the corresponding L2 space. Okay, but then if you take free products of such things, I mean, that's the thing which can also be done, but which I wanted to avoid, because this is getting much more technical. Good, okay, so I think that's what I wanted to say about this analytic machinery. Okay, and so now we have the Christmas break, so no classes for 2 weeks, but after this I want to address then 2 more big topics. I mean, one is the random matrix connection of free probability theory, and the other is the use of free probability theory for von Neumann algebras. Okay, so that's the 2 main topics which we will treat after Christmas. Good, okay, that's it.